So here in addressing mode, you have to remember only the subtopic, and you can easily explain all these subtopic because everything, all the explanation is in the name only. Here the immediate addressing. Immediate addressing, by the name you can easily understand, you can easily remember this example, add 5. So add 5, this 5 value will be added with the accumulator value, right? So why it is immediate? Because immediately the value is given here. Generally, you have seen we provide a reference. This is opcode and this is operand. So for the operand, we provide a reference. Reference for a memory location, reference for the data, reference for the register. But here, we are not providing reference. Here, we are directly giving a value, that is a 5. So that's why we can say it is an immediate addressing. And here in the diagram, because you could see opcode and operand. Opcode is add and operand is 5. Direct addressing. In direct addressing, here the instruction is your opcode and here is operand, and operand there is an address A. Address A is the reference for the memory location A, and on memory this is the memory location A, where actually, so here again you will find it is a direct kind of addressing. Directly you are getting a reference of a memory location. Next one is indirect addressing. So why the direct and indirect, you can easily remember by this diagram. In last lecture we have discussed. Like here, you have a reference of memory location, but actually on that memory location there is no any kind of operand is available. But actually that memory location point to the operand. So it is like an indirect, because directly you are not getting the operand value from the memory. That location actually pointing to the another location where actually operand is stored. By this technique, number of instruction can refer the same operand. So indirect addressing. Registered addressing. In registered addressing, instead of memory, here you will find there is a registers. So as you know, on a processor, there are the registers are available, the general purpose register that we use for the arithmetic operation. So here, this instruction is referring the registers R1, R2. Even in assembly language program, you will find mainly they use this kind of register addressing, in which you will find the instruction is there as well as the register addressing is there. So here the register address on respect to register operand is stored, and this instruction pointing to that operand. Similarly, registered indirect addressing. In registered indirect addressing, first you are pointing to the register, and the register point to the respective memory location on the memory. So in the last lecture, actually, we have discussed what are the advantages of direct, indirect addressing mode. Here it is displacement addressing. Displacement addressing means here is the address and here is register, pointing to the register. So the address A, you are getting a value, and from the here you are register R, that is a registered address, and this registered address point to the operand. And but here actually when you will calculate the address and this location, you will get the particular location on the memory. So displacement, it having a number of types, like a relative addressing, base register addressing, index addressing and stack addressing. So in last lecture, actually, we have discussed up to this. Now we'll start the next topic, that is instruction format. So see here, as per the unit name, that is instruction set, whatever our discussion is completely related to the instruction only. And even whatever we are discussing, if you logically think, everything is known to you. So by this way, actually, you have to remember each and everything. The concept is very simple. Now here, instruction format. So even you have used this instruction format while doing a programming. But here we are considering mainly the assembly language programming. So in assembly language program, mainly we use this kind of instruction. So here, the instruction format, already many times I have discussed with you. This opcode is there and operand is there. So opcode is, for example, opcode is add is our opcode. This add is our opcode. Add is our opcode, and the operand reference could be your A and B. This operand reference could be the A and B. So here actually, this opcode means what kind of operation you want to perform on A and B. And this A and B is what? A and B is actually giving you reference. Reference of, we have seen in our previous topic, what kind of reference actually it gives you. It gives you reference of the particular memory location or the register or the another memory location where actually that memory location point to your operand, or it can be the value, right? So here, this operand reference, suppose here it is A, so at particular memory location A, some value is there, so it will consider 10. For example, B is 15. So add will perform addition operation like this. So simple, this is the instruction format, and it include opcode and operand. Now this operand many time implicit or explicit. So yes, many time we explicitly specify in an instruction, like here we have explicitly specified add A, B. It means we have to add A and B. And many times we write the instruction like this way, like add A is enough. So here actually we can say at this moment, add A means here whatever the value is there, this value will be added with the accumulator value. So this time we can say implicitly there is another value is there. Explicitly we are not specifying any kind of value here, but implicitly actually we are performing addition operation, because in the accumulator there is another value and we are adding that accumulator value with A. So sometimes we provide all the operand, and sometimes you will find there is only one operand and you are doing the same kind of operation. So in this topic, actually, you are going to learn what are the different types of instruction format, how actually different way we can use the same instruction. So usually more than one instruction format in an instruction set. So obviously you can perform any kind of operation with the different way, because the different types of instruction formats are available, and by that instruction uh, format you can perform uh, your task in different way. Now we will first consider like the three address instruction. So by the name only you can easily understand a three address instruction means, obviously in instruction there are three addresses, right? So here add R1, R2, R3. So the three address location reference is provided here. This is reference 1, reference 2, reference 3. It is pointing to the one memory location. It is pointing to the another memory location. It is pointing to third memory location. And actually this is your opcode. What kind of operation you want to perform on? These are three addresses. So here you want to perform addition operation. So automatically what your system will do, it will add R2 plus R3, and whatever the result is there, that result will move into the R1. So this is the instruction, and what kind of operation will be performed? So here you can understand, here this type of operation will be performed, like R2 plus R3, and the result will store into the R1. The two address instruction. So this is a one format of three address instruction. The another format that is a two address instruction. In two address instruction, we are not using the three memory references. Two address means two memory references are there. So the same way actually you can perform addition operation here. So how you can perform addition operation? Like R1 plus R2, and whatever the result is there, it will be stored into the R1. Right? So in this way actually we can perform the same addition operation by using only the two addresses. The same addition operation even you can perform by using only one address space. So here add M. M is, there is a memory location. This M is pointing to the memory location. Memory location. Plus, as I told you, if there is only one address reference, that time whatever value is there, this M is pointing out to, for example, 10. So this 10 will be added with the accumulator. So according to this rule, this whatever the value is there, it will be added with the accumulator value, and your result would store into the accumulator only. So one address instruction. Now zero address instruction. And many times here you will find we are not using any kind of memory address reference. So actually here you will find there is only one address, but obviously to perform addition operation, multiple address locations required. But here implicitly we are using this location, but explicitly we have not written here. Like here explicitly we have written how many memory location required. Here implicitly actually we are using accumulator and performing the same operation, but explicitly we are not writing here. Zero address instruction. In zero address instruction, here you will not find any kind of address, only the add. So to use this kind of to execute this kind of instruction, we can use a stack. We can use a stack. So in stack, we will push the stack concept you will learn, I think this year or the next year. So So if you will see, yeah, you will find this kind of stack. This is like a stack, and in a stack, we'll perform operation. We will push a value into this stack. So here is, for example, this TOS means of the stack, top of the stack, and this is top of the stack -1, top of the stack -1. So here actually you perform a addition operation. So first you will push into the top of the stack, and then you will perform addition operation, and you will get the result. So here actually we does not require any kind of memory reference. Here explicitly, actually, obviously for all kind of operation require memory reference, but explicitly we are not writing any kind of memory reference over there. So that's why we call it as zero address instruction. So 3 address, 2 address, 1 address, and 0 address. Now suppose if you consider one equation that you want to suppose we consider one instruction that you want to perform the addition subtraction operation by using these different types of instruction format. So this is the example that we have considered. In this example, we have to evaluate a plus b into c plus d. This is our equation. Now we'll see if this equation is there, how you can evaluate this equation by using the 3 addresses. Then we'll see how actually you can evaluate this equation by using 2 address, 1 address, and 0 address. So concept is very simple. Now 3 address memory reference is available. So that time what you will do, directly you will perform addition operation like AB. You want to perform addition operation AB, and the result would store into the R1. Because the 3 memory locations are available, you can easily utilize all these 3 memory locations. So add is your opcode, what kind of operation you want to perform, addition operation. So by this, the addition operation will be performed on A and B, and the result would store into the R1. This is the explanation actually what is going on here. So at a memory location A, whatever the value is there. So that's why memory location at A plus memory location at B. For example, here it is 10 or here it is 5, 10 plus 5, that is 15 will be stored into the R1. And this is your actual instruction. In actual instruction, you will find there's a 3 addresses are there, R1, A, and B. And this is the explanation actually. And this is your actual instruction. So actually this part completed. Similarly, the second part, C plus D. So add R2, CD. By this instruction, what will happen? This is the explanation actually, what actually will be performed here. So C plus D, whatever at memory location C plus memory location D, it will be added, and the result would store into the R2. Now R1 and R2 is calculated. Now we have to multiply. So it is very simple. Multiply X R1 comma R2. So after R1 R2 multiplication, the result will be stored into the X. The same explanation is here, what kind of operation will be performed. So actually this is your instruction. So by using 3 addresses, we can evaluate this equation. Suppose the same, instead of 3 address, if there is only the 2 addresses. So how actually we can evaluate this equation? So we'll see. So 2 addresses are there. So temporarily actually we have to store our value into the temporary memory location. And then we'll transfer our result into our required register. So at the very beginning, first we have to move this A value into the R1. So see here, if at memory location A, for example, there is a 5. So this 5 will be assigned to the R1. So A is assigned to the R1. Similarly, now we have to perform addition operation with A. So add R1 comma B. So that R1 is holding a value. That value, whatever value is there, that value will be added with the memory location at B. So at memory location B, if there is a 5 is there and R1 5 is there, so R1 plus memory location at B, 5 plus 5, that is a 10. So R1 is 10. Similarly, moves R to C. So C value will be moved to the R2. Then we will perform adding operation with the R2. So add R2D. By this instruction, whatever at memory location D, that value will be added with the R2 and result will be stored into the R2 only. So R1 and R2 is holding the A plus B and C plus D value. So then we will multiply R1, R2. So MUL for multiplication, R1 comma R2. By this way, the multiplication occur. So here, after the multiplication, your result would store into the R1. Now we have to move this result into the memory location at X. Very simple. So we have seen how we are discussing actually different instruction formats. The 3 addresses, the 2 addresses. Even you might have used this kind of concept in your C programming, right? You use 2 variable, 3 variable, some, right? So similarly, by using 3 variable, 2 variable, 1 variable, or we can say 1 address. Now if it is 1 address, obviously if it is 1 address means accumulator required. So first we have to move this A value into the accumulator. So load A. So whatever at memory location A, that value will be loaded into the accumulator. Then at memory location B, whatever value is there, that value will be added with the accumulator and result would be stored into the accumulator. So accumulator is holding a result. That result we have to store into the temporary location. So store T, a temporary location, because again we have to calculate C plus D. So then first we have calculated A plus B, and now that A plus B result we have to store on temporary memory location. So TM, temporary memory location. So the A plus B result stored here. Now similarly C plus D. So load C, it means whatever the memory location C, it will be loaded into the accumulator. Add with the D, so that whatever that memory location D will be added with the accumulator and result will store into the accumulator. Then we have to again, so here if you see accumulator is holding C plus D value, and at memory location T is your holding the A plus B addition operation. Now what we have to do, we have to multiply both. So here we will multiply accumulator plus memory location at T, and result will store into the accumulator. And then we have to store accumulator result into the memory location at X. Actually, one student have a doubt. He is saying me to repeat the 1 address. Actually, that's why I have taken too much time on our the previous unit number 1, the diagram, in which we have seen the processor have the 1 accumulator AC, right? AC is 1 memory location is there, It is one kind of register is there. So actually, accumulator we are using here implicitly. Explicitly, actually, you have these memory locations are available like A, B, C, D. These are the memory locations that are available. Now this A is there, and you are using only one address. How much address you have? Only one address. So this is the our situation. We have only one address, and by default there is an accumulator is there. Now how actually you can calculate, how evaluate this equation? So what you have to do first you have to load this value. For example, A. First you have loaded A, na? So this value is here at memory location A. So it occupied one memory location. Now you have to load B. So how actually you can load B? First you have to move this A into the accumulator. So when you will move this A into the accumulator, this space will free, right? So now accumulator is holding A. Accumulator is holding A. And now this space become free. Now then what we are doing here, so memory location at A loaded into the accumulator. So this is the accumulator, here it is loaded, and one address space you have. So this is free now. Now what we have to do, we have to add. So this is free now. So you will load this B here. So this is your one address space memory location. So this B loaded here. Then we will perform the addition operation with accumulator plus memory location at B. So the addition operation will be performed, and this result we will store into one temporary location, temporary memory location. And after that, immediately we will move this result into the accumulator. So that's why accumulator plus MB and result will store into the accumulator. So now accumulator is holding A plus B, and then we are moving this accumulator result into the temporary location TM. So A plus B loaded into the TM, a memory location at T. Similarly, we will perform the same kind of operation on C plus D. So accumulator is holding a C plus D addition. So this accumulator is holding C plus D. Now we have to multiply. So at memory location T, there is A plus B, and is in accumulator is holding C plus D. So we have to multiply both. So that's why at memory location T into accumulator, and that multiplication result will store into the accumulator, and this accumulator result will move into the memory location X. In this way, even by using, we have only one address, but still we can evaluate the same equation. Now, suppose we have 0 addresses. We don't have any kind of address. That time we have to use a stack. In a stack, actually, we have to, this stack is like this. So in a stack, if you are pushing a value, suppose if you have added 1, 2, 3, 4, and if you are popping a number, so what you will get first? 4, then 3, then 2, then 1, right? So It's called, we can call it as first in, last out. First in, last out. Similarly, there is another concept that is a queue. You might have learned in another data structure subject, or you will learn, that is a queue. In queue, suppose if you are pushing a value, do you know this stack queue concept? Have you learned in any subject? Dear students, do you know stack and queue concept? I think data structure, this concept might have covered, right? Do you have data subject this semester? Okay, okay. So right. So see here, we can use this stack and queue to perform the same, to evaluate this equation. How actually we can use this stack? TOS means top of the stack, obviously. If your first element is A, obviously it would be the top of the stack. So first we push A into the stack, then we will push a B. When you will push a B, B is on top of the stack, right? Because A is the first one, B is the second one. So now B is on top of the stack. Then we will perform addition operation, A plus B, and after addition, we are putting this A plus B addition value on top of the stack. Again, it is top of the stack. Then we will push C. Then again, we'll push D, and then we'll perform a C plus D. And then this value is on the top of the stack. So finally here, the stack is like this. This is a, for example, stack. So here it is holding A plus B value, and the second is holding a C plus D value. Now C plus D is on top of the stack. Now we have to perform a multiplication operation. So C plus D into A plus B. So how actually we can perform? We will pop both the values, pull both the values, and we will perform multiplication. And after multiplication, we will push our result on top of the stack. So it is very simple concept. So after addition, after multiplication, the value is on top of the stack, and then we will pop our result and store into the memory location X. At the X is holding your final result. Now here the concept is like a zero address, but actually here we are using addresses. But why actually we are calling it as a zero address, one address, two address? Because explicitly we are not writing any addresses here, but implicitly we are using these addresses. Here you can understand actually, here we are giving only one address reference. Explicitly we are giving only one address reference. Here we are giving two address reference. Here, three address reference. Like that. So you can evaluate the same instruction the multiple way. Similarly, RISC and CISC we will discuss in later what is exactly RISC and CISC. But suppose if you want to perform the same operation in RISC. So how we can perform in RISC? We will load this A value into the R1, R1, R2, R3. These are the general purpose registers which are available on the processor. So first we will move this A value into the R1, then B value into the R2, C value into the R3, and D value into the R4. Now we have A, B, C, D, all the values in these respective registers, R1, R2, R3, R4. Now we have to perform this operation. So A plus B. So what we will do, simply we will add R1 and R2. And similarly C plus D, R3 and R4. So the R1, R2, it means after addition, the result would store into the R1 like this. R1 plus R2, and the result would store into the R1. R3 plus R4, result would store into the R3. So R1 and R3 is holding addition. Now we have to perform a multiplication. So again in multiplication, MUL multiplication, R1, comma R3. So R1, R3, after multiplication, the result would store into the R1. So here, the result would store into the R1. Then the R1 is holding a complete answer after the evaluation. So this R1 value will move into the memory location X. So store X. So here, in this way, the RISC evaluate this instruction. So the concept is very simple. The instruction format, then operand, reference 1, reference 2. And there's a 3 addresses, 2 addresses, 1 addresses, right? And 0 addresses, RISC addresses. In this way, actually, you have to explain. Now, the next topic is instruction execution. Already many times, actually, I have explained this diagram. But again, unfortunately, or you can say fortunately, the same topic repeated in unit number 2. Instruction execution. As the name is instruction set. So without this topic, your unit cannot be completed. So that's why they might have added this topic in unit number 2 again. But I want to ask you to explain again this diagram.